Okay, thank you. My name is Johan Kwisthout from the Donnes Institute for Brain Cognition and Behavior, Radboud University in Nijmegen. And I'm talking about neuromorphic complexity analysis. I brought up a picture here by Scott Aronson, who is a quantum complexity theorist. And the picture to the left shows you a sort of a hierarchy of complexity classes that are motivated by the sort of problems that they can solve. So in the middle you see the complexity class P, consisting of problems that can be efficiently solved by a classical computer. Then you have the class of problems solvable by a quantum computer. And then you have these larger classes MP and P-space. You see the blue dot are the MP-complete problems, the hard problems that cannot be solved in polynomial time by traditional hardware. And to the right, you see the brain skills machine who is thinking, where do I fit into this picture? What sort of problems are efficiently solvable by neuromorphic hardware? So the question is, are these problems, are these really different, or are these the same as the problems that we can solve by a traditional von Neumann architecture? And the simple answer to this question is, we cannot hope to solve NP-hard problems in polynomial time with arbitrary precision. So in that sense, the question is easily answerable. No, we cannot solve NP-hard problems. There is no free lunch in complexity theory. But there are much more interesting questions. For example, are we asking the right question? So if we're talking about Turing machines, we're talking about cells, and we're talking about state transitions, about space and about time. Maybe we should talk about efficiency solvable in the sense of energy efficiency, the amount of energy that our machine uses in order to solve a particular problem. And the question then arises whether our current models of computation in traditional Turing machines, whether these suffice to answer these questions. And the rationale behind this question is, for example, that we're dealing with a non-von Neumann architecture. To the right, the top on the right, you see the picture showing this model where you have this bottleneck between memory and the CPU, and contrasted to the bottom right, where you have lots of cores, where you have a memory and a program together. It's a different sort of architecture, not well fitted onto the Turing machine. We also have energy as a bounded resource. So there's this well-known gag that the brain uses amount of energy that is comparable with a light bulb. If we want to simulate the brain with a supercomputer, we need several megawatts of energy. Well, that comparison is not entirely fair because that's a simulation and it's on a general purpose computer, but still it's very tangible that there is a huge difference between energy consumption of the brain and energy consumption of a simulation of the brain. So the energy as a bounded resource becomes ever more important given this Turing bottleneck and heat consumption in the chips. In traditional Turing machines, a 0 and a 1 are interchangeable. A Turing machine doesn't really care about whether it's computing with a 1 or a 0 every bit is equal in this sense, and that is not so the case in the brain, because a spike costs a lot of energy and the absence of a spike costs way less. So it's important for a brain to minimize the amounts of spikes that are necessary to accomplish a particular task. So we want to take that into consideration, the amount of spikes that are really necessary to solve a problem. And finally, of course, we have a noise and randomness as a resource. So the brain is not a deterministic computer as a Turing machine is. The brain is a stochastic computer in a sense that where neurons fire stochastically and where there is noise, and that can be used as a resource for sampling to obtain better computations. So what we proposed is, in line with an earlier proposal by Wolfgang Maas at a Dark School seminar, to use networks of spiking neurons as a computational framework to capture the power and the energy efficiency of neuromorphic hardware. The key aspects of these neuromorphic machines are here. There is collocated memory and computation. There is learning and adaptation as well as training and programming going on. Noise can be used as a resource for sampling, and there is a spiking behavior. So the absence of a spike and the presence of a spike are different, and that is useful for our paradigm. It's also fruitful that these neural spiking networks are firmly rooted in a large body of theoretical work, computational theoretical neuroscience. So what sort of open issues and research questions are we working on? So for example, the relationship with more traditional models like probabilistic Turing machines and threshold circuits with an energy complexity function. So these probabilistic Turing machines, they deal with stochasticity. They have a different model of acceptance that deals with probabilities. They have the problem that they don't capture energy efficiency. These threshold circuits do, but they don't have the capacity to deal with noise as a resource. We are interested in complexity classes, so we also want to make a sort of a hierarchy of complexity classes and looking at what makes a problem hard, especially whether there is sort of an energy hard problem, a problem that cannot be solved with a limited amount of energy in principle. In a similar vein as we have, for example, p-complete problems that are inherently zero, that we cannot effectively parallelize. For example, linear programming is such a problem. So we want to find out what sort of problems are energy hard in that sense. Of course, we want to do structural complexity theory, so reductions between classes, how to reduce a problem to another problem, to prove hardness, what sort of way would we need in order to prove hardness. And we need a notion of acceptance criteria, for example, the stability of a distribution, the time we need for convergence, and energy limitations for solving a problem. So the conclusion of this very brief lightning talk, I have a poster here for discussion, is I think best shown here by this quote from the Department of Energy workshop report, that there's likely that an entirely new computational theory paradigm will need to be defined in order to encompass the computational abilities of neuromorphic systems. We want to step into that particular niche. We want to help contribute to that new computational theory and paradigm. And the applications here are that we want to describe what sort of problems can be effectively solved on neuromorphic hardware and what sort of problems resist such solutions. And we want to use this machinery in order to describe the fundamental limits of the brain's cognitive capacity given the limited resources that are available in the brain, notably the limited amount of energy that the brain has to its disposal. We're very open for feedback and suggestions. This is very much work in progress. We have some limited technical results that relate, for example, computations on probabilistic machines to networks on spiking neurons. And we see that the sort of limitations that arise in these probabilistic Turing machines also arise in spiking neurons when we look at, for example, time and space behavior. But energy is really a new player into time. We really need to look into energy efficiency in order to really get a grip on the power and the limitations of neuromorphic machines. So thank you very much.